Hello everyone and welcome back. It's ichino-ani here. Today is April 13th, a lovely Sunday. And guess what? I found a super interesting paper trending in the arXiv for us to explore. It's from the field of machine learning, or I guess the grown-ups call it. The title is on Vanishing Variance in Transformer Length Generalization. Wow, that sounds complicated, doesn't it? The clue is chance or board 4.8 storage of 4.2827 time. It's quite a long address. So let's break this down, shall we? You know those super smart AI models, that the ones that can chat or write stories. Many of them use something called a transformer. Think of it as their brain. But there's a little problem. These transformers are often trained on, let's say, short sentences or short pieces of information. But when we ask them to read a really long story or process lots of data at once, they sometimes get confused. Like, they don't generalize well to longer sequences than they saw during their training. This is called the length generalization problem. It's like learning to count to 10, but then struggling to count to 100. Now, this paper has a really neat idea about why this happens. They call it, vanishing variance. Imagine you have a bunch of numbers, okay? Variance tells us how spread out those numbers are. Or are they all clumped together? Or are they all different? What the researchers found is that inside the transformer's brain, in a part called the attention module, something funny happens. As the sequence of information gets longer and longer, the important signals or outputs from this attention pod become less spread out. Their variance decreases or vanishes. This makes the information look very different from the shorter sequences the transformer learned. It's called a distribution shift. The model sees data that feels unfamiliar, which makes it harder to understand. So what did these clever researchers from the University of Oxford suggest? They tried adding something called layer normalization right after the attention part. Think of layer normalization like a helpful tool that keeps the numbers nicely balanced. It helps to keep the average and the spread, the variance of the signal is more stable even when the sequences get really low. And guess what? In their experiments, using tasks like finding the biggest number in a list or looking things up like in a dictionary, letting layer normalization helped the transformer handle much longer sequences better. It reduced the tricky distribution shift, but it didn't completely eliminate it. Okay, so why should we care about this? Where might we see improvements? Well, think about this. First, imagine asking an AI to read a very long book report and give you a summary. If the AI can handle long text, the summary might miss important stuff from the end. Better length generalization means, second example, by AI helping programmers write really big complex computer programs. That's a super long sequence of code. If the AI gets confused by the length, it might make mistakes. This research could help AI become better coding buddies for big projects. And third, think about predicting things like the stock market, or maybe even the weather far into the future. This often needs analyzing long histories of data. If the AI model can't generalize to these long time periods, its predictions might be wrong. So this could lead to better long-range forecasting. Now, other researchers have tried different things to fix this length problem, like changing how the model understands positions in the sequence or tweaking the attention mechanism itself. But this paper gives us a new angle, focusing on this vanishing variance idea and how layer normalization can help stabilize things. It seems layer normalization is a useful trick that works alongside other methods too. The paper does mention that they used a simpler, one-layer transformer for their tests. So, more research is needed to see how well this works in the really big, complex metals we use every day. It's a really cool step towards making AI better at understanding long streams of information. That's our paper for today, everyone. Isn't it fascinating how they're teaching computers to handle bigger and bigger challenges? Keep thinking, keep exploring, and I'll see you next time. Bye-bye.